Welcome everyone. Today we are continuing our discussion on hypothesis testing. And so last time we went over, I started talking about basics of hypothesis testing and how we need to be able to go from words to symbolic form. And so it's very important to be able to identify the key words in our sentence that give us the different forms. We need to know what parameter we're testing. We need to know the inequality we're using. And so based on our setup, that's how we know what our test statistic is, and that's how we can continue with our hypothesis testing. So the setup is so important. Today I'm going to continue. I know I did an example with hypothesis testing in our last lecture, so I want to just do one more so you have a little bit of a review. So let me switch you over to, I'm going to try to jump to that example without having you go through all the in-between slides. I think that's the one. Okay. So this example says to use the p-value method, but what I'm going to do is I'm going to use the traditional method just because I want to review the traditional method. And so that's what you'll see me do, okay? All right. Here we have Gregory Mendel, who conducted his famous hybridization experiments with peas. And in one such experiment, resulted in offspring consisting of 228 peas with green pods, and then we had 152 peas with yellow pods. So we had yellow pods and we had green pods. All right, so the green pods, we have 428 of them. So I'm going to write 428 here, and we'll put a G there just to remember those are the green ones. And then we also had yellow. And for the yellow pods, there were 152 of them. Now, according to Mendel's theory, a quarter of the offspring peas should have yellow pods. So we're using a 0.05 significance level to test the claim, and so that's how we know it's a hypothesis testing question, because it's telling us to test the claim. Test the claim that the proportion, and that's also important there, we need to know what that means, that the proportion of peas with yellow pods is equal to 1/4. All right, so again, we need to be able to figure out which population parameter we're talking about here. So we have three to choose from. We have mu, we have sigma, and we have p. So based on the information that's given here, what population parameter are we testing? Can you type out the population parameter you think we're testing? Okay, so we're testing P. Good. Okay, so then we have to say something about P here. So P is represents the proportion. And it says the proportion of peas with yellow pods is equal to. So now we have to figure out what inequality we have to use. So is equal to 1/4. So now that you know the population parameter we're using, now we have to write it in symbolic form what this means. So the proportion of peas with yellow pods is equal to 1/4. And 1/4 as a decimal is 0.25. Okay, so is would be equals, equality. Okay, so I'm just going to erase what I have here at the bottom. All right, so if I continue here, I'm going to go ahead and set it up. Here's the null and here's the alternate. So one of our steps is to set up our hypothesis, and we break it apart into the null and the alternate. And remember, the null is the HO, the alternate is the H1. So the null and the alternative is what I should say, alternative hypothesis. Okay, so this one has equality. So if your claim has equality, do you remember where it goes? So our claim has equality. So where does it go? Okay, so the claim sometimes goes in the null and it sometimes goes in the alternate. It all depends on the inequality. So yes, equality means that the null, in this case, the equality means that our claim is going to go in our null hypothesis. So P is equal to 0.25. That's where our claim is. What is the opposite of equality? Whatever the opposite of equals is, that goes in the alternate. So in the alternate, you have P not equal to 0.25. All right, now the next step is your test statistic. So I'm calling this TS for test statistic. So my test statistic depends on the population parameter that's being tested. So we had many formulas for test statistic. So let's see which one I have to use here. So this is from your Chapter 8 summary that's already posted on your lecture notes. And this is the first page of it. But I do have a list of test statistics for you. Again, it all depends on the population parameter being tested. So since we're testing P, population proportion, then you need to make sure you're using the corresponding formula. I'm just going to go ahead and copy that formula onto the next page. All right, so I'm just copying that formula down. So we have Z is equal to P hat minus P. And that's going to be divided by the square root of P times Q over N. Now, I don't know what N is yet, and I do not know what P hat is. Okay, so let's figure that out. So we need P hat, and we also need N. So N is our sample size. While we have green pods and yellow pods. So we have 428 P's with green pods and 152 P's with the yellow pods. So in total, we have to add our green and our yellow pods to get our total number of pods. Okay, and so what do we get here? 580, right? All right, so that's the total number of pods. P hat is X over N. So the claim is talking about the yellow pods. So we are testing the claim that the proportion of P's with the yellow pods is equal to 0.14. So when I write P hat, it has to be in terms of the yellow pods. So out of the 580, how many of them happen to be yellow? Well, that's what you use to come up with P hat. So how many yellow do we have? All right, so I'm writing it as a this is my fraction. That's my P hat as a fraction. Now you know that the fraction is the exact representation of P hat. So when you leave your P hat as a fraction, that's the exact representation. But if you write it as a decimal, then you are rounding it. So you have to be careful about rounding. Whenever possible, use the fraction. But if you do not like to work with fractions, or for some reason it's easier to write it as a decimal, then I would say round your P hat to about 4 or 5 places. So if you take 152 and divide that by 580, I get about 0.26207. Point two six two zero seven. All right, so that's the information that I need to plug everything into my test statistic. Okay, so I'm going to take p hat, and I'm leaving that as a fraction, 152 over 580. If you want to put the decimal format of that, the 0.26207, that would be okay too. I prefer to use the fraction, so that's my p hat, minus p. Now remember that this test statistic, when I calculate the test statistic, it's under the assumption that the null hypothesis is true. So then for p, I have to enter the value of p in the null hypothesis, which is 0.25. So p is the value in the null hypothesis. And then in the denominator, I have the square root of PQ. All right, so I know what P is. That's 0.25. That's the value in the null hypothesis. But what do I know about Q? What should I use for Q? Does anybody remember? How do I get Q? Was it given to me in the problem? Or should we already know it? Okay, right, we should know that. It's the 1 minus p. All right, so we have 0.25 and then we have 0.75 because it's the 1 minus p to get q. And it's 580. Okay, so when you are putting this in your calculator, you want to make sure that the numerator is in parentheses. And then with the square root, it does give you a parentheses already to begin with. But just we want to make sure the numerator is in parentheses, it stays together, and the denominator stays together. All right, so go ahead and plug that into your calculator and tell me what you get. Now remember, the z-scores are always rounded to 2 places. You want to make sure you round to 2 places after the decimal. All right, so does everybody agree with that 0.67? So we have 2 people who say 0.67. Sounds good? Okay, if you're getting something else, let me know and we can work it up. I can bring up the calculator. All right, 0.67, okay. So your z is equal to 0.67. Okay, so you run into 2 places. Okay, so we have one person who's getting 0.75 Okay, so you want to make sure you check all your numbers, and I used the fraction, so hopefully you did too. But even if you didn't, you should have ended up with the same. With the same value. Okay, so remember in the numerator I put parentheses, and that was 152 over 580. That was my p hat. And then to that I subtracted p, which was 0.25, and that's my parentheses, and then I divided by the square root. And then the square root I had p and q. So p is 0.25 and then q is 0.75. And don't forget to divide that by your n. Now on my calculator I have to press the right arrow key so that I get out of the square root. And so by doing that, I'm going to go ahead and press enter, and that's what you end up getting. So just make sure that you typed everything in correctly. Make sure all your parentheses are where they should be. Forgot a decimal. Yeah, it's very easy to forget. It's to forget something there. So you want to make sure you double check your work. Okay, so we're good. 0.67. We all agree on that. Okay. The next step, remember, where I'm doing the traditional method. I know it says p-value method here, but I'm going to use a traditional method first. And the reason I'm doing that is just for review purposes, so you remember what we did last time. Okay, so let me emphasize that I'm using the traditional method first. Okay, so then we are at step 3. Step number 3. So in the traditional method, step 3 requires that I look at my critical values, my critical region. So I have to determine whether this is a left tail test, a right tail test, or a two-tail test. So what do you think I have here? Left-tailed, right-tailed, or two-tailed? So where do you go to find out what kind of test this is? You have to always go back to your alternate hypothesis. So in our alternate hypothesis, you have not equal to. So because you have not equal to, this right here tells you it's two tails. Okay, good. So some of you said two tails. So that's how we know it's two tails. If whatever inequality is in the H1, always go back to the H1. And this doesn't have to do anything with your claim. Your claim could be in the null or in the alternative hypothesis. Doesn't matter where the claim is. You always go to the H1, to the alternative hypothesis. Here it's not equal to, so we have two tails. All right, so this is our critical region. And I have to find my critical value, which are the values that separate the shaded region from the non-shaded region. Okay, so I'm trying to find my critical values. So I call these my CVs, my critical values. Now alpha is the area in my critical region. Were we ever given alpha in the problem? Do we have alpha in the problem? What is alpha? All right, so the significance level is your alpha. Good. All right, so alpha is 0.05. So our significance level is alpha. And so in this case, alpha has to be shared between the two tails. So alpha is the area in the shaded region. So to find out the area in each tail, what would I have to do to alpha to find the area in each tail? Okay, so then if I divide by 2, I get 0.025 then, right? Okay, so the area in each tail is 0.025. So again, I'm trying to find my critical value. Alpha is the area in my tails. Because I have 2 tails, I have to divide it by 2. I only divide by 2 when I have 2 tails. Okay, so the critical value, you have to obtain that from one of your tables. So we have table A2, A3, and A4. So you have to decide which table is appropriate here. Do we go to A2? Do we go to A3 or to A4? What do you think? All right, well, look at what we have here in the in our test statistic. It starts with a Z. So that might be a clue as to which table we can go to. All right, so let's try table A2. All right, so table A2 is where your Z's are, right? That's your standard normal distribution. Because our test statistic starts with the Z, that's a good way of remembering which table you use. Now the test statistic we're using depends on the population parameter being tested. So P is being tested, so that's why we're using this particular formula for our test statistic. It happens to have a Z in there, so that's a good way of remembering where to get our critical value from. So table A2. All right, so in table A2, you're looking up an area. The area in the tail is 0.025. So remember, you're looking up an area. So table A2, that you want to make sure you're in the body of your table because the areas are in the body of the table. So here's my table. On your screen, hopefully you see your table A2 that I have here for you. So I am looking at 0.025. I think we said 0.025. So 0.025 is in the body of it's in the body of your table. All right, and it just happens that it's right there, 0.025. So now you work your way out to find the corresponding Z. So that one would have, if you're working your way out, it looks like it's negative 1.9, and then on the top, negative 1.9, and then there's a 6 here. Negative 1.96. Negative 1.96. All right, so that's our Z. And here, we call it a critical value. So right now, you should be back on the whiteboard, and I'm going to write 1.96. Now, notice that I am to the left, so it has to be negative 1.96. What do you think the other one is? We have 2 critical values, right? And we know the distribution is symmetric. So if you have one, you should know the other. Good, okay. So our critical values here are 1.96. Now, in order to know what your critical values are, you have to go to one of your tables. And here we went to table A2 because that's where our Z's are. Okay, so I am going to take my test statistic and I'm going to compare that to my critical values. So is that test statistic in the critical region? That's the question. So here's my test statistic. I'm trying to find out if that is in the critical region. So 0.67. That's pretty close to the middle, right? Close to 0. So it's not. You're right. It's definitely not in the critical region. So with the traditional method of hypothesis testing, we are comparing our critical value to our test statistic. You're comparing your critical value to your test statistic. If your test statistic falls in the critical region, which is the shaded region, then you reject. But in this case, we're not rejecting. In this case, we're going to fail to reject. So if we fail to reject the null hypothesis, do we still believe the null hypothesis is true? We're failing to reject the null hypothesis. So if we fail to reject it, do we still believe it's true? All right, so we just failed to reject the null hypothesis. So we failed to reject the null hypothesis. We did not reject it. We did not have strong evidence to reject, so we failed to reject. Yeah, so that means that we continue assuming that the null hypothesis is true. We did not reject. We failed to reject. So we're still working under the assumption that the null hypothesis is true. There's not enough evidence to say otherwise. So remember, your conclusion either says you're going to reject the null or fail to reject. Those are the only two options you have. In this case, our test statistic does not fall in the critical region, so we have to fail to reject. Okay? All right, so we have to write our conclusion using one of the we have to make sure we're writing our conclusions so that anyone who does not know statistics, that they can understand what's going on. So I remember last time I showed you a summary here for it's all my conclusions. So I'm looking at that pull-out formula card that came with your textbook, and it's also in your ebook. And it looks something like this. Those are the conclusions that you can choose from. All right, so I'm going to copy this over so we can write on it. This is the wording of our final conclusions. So that's what I'm putting on for number 4. Okay, so number 4 says, does the original claim contain the condition of equality? So now I have to go back and see where the claim was. Did the claim have a condition of equality? So if I look here for my claim, did it have equals? If it did have equality, it would have been in the null. So did the claim have the condition of equality? All right, it's right here. Good, okay. So yes, it did. So let's follow the yes. Do you reject the null hypothesis? Let's see, did we reject? No, we failed to reject. All right, so we failed to reject, so then no, the answer to that is no. So I follow the no. So it looks like my conclusion has to look like box number 2. Box number 2 says there is not sufficient evidence to warrant rejection of the claim. So we're going to write that out. There's not sufficient evidence to warrant rejection of the claim. Now I'm going to take a break from writing with this pen and see if I can type it out. One of the advantages to having this is that I can type, maybe. All right, so there is not sufficient evidence to warrant rejection of the claim. I think that's what we had said. Notice that as I'm typing my conclusion, I'm not using any symbols. I'm not using any symbols. All right, so there is not sufficient evidence to warrant rejection of the claim that the proportion of peas with yellow pods is equal to 1/4. So the conclusions should be easy. It should be easy to understand. So if someone who does not know statistics, if they go and read the question and then read the conclusion, they understand what's going on. So in this case, the sample evidence is not strong enough for us to reject the null hypothesis. So we still keep believing the null because our sample data didn't tell us otherwise. So the theory was that 1/4 of the offsprings would have yellow pods. So that theory is still something we continue to believe because in this case, the sample evidence didn't tell us otherwise. All right, so I'm looking at box number, making sure I wrote I know there's something missing there. I forgot the very important part here is the word no. There is not. No, I left it there. There it is. There is not sufficient evidence. Let me capitalize that. And if I can, I did put it in there. There is not sufficient evidence. It didn't allow me to take it out. Okay, I just wanted to capitalize that. So there is not sufficient evidence to warrant rejection of the claim. I'll just make it bigger. Right, it's very important for you to make sure you're writing your conclusions. Go back to the question and read it to see what the claim was, because after all this work, you probably forgot what the claim was. All right, so that is, I did this example, that's in your notes, but I didn't use the p-value method. Instead, I've used the traditional method, and I did that only to review what that traditional method was. I only did one example last time, so I just wanted to take time to do this one more time. Okay? So with the traditional method, you're always comparing your test statistic with your critical value. The alpha that's given to you is always the area in the tails when you're trying to find your critical value. So this problem, I'm going to repeat it, and instead of using the traditional method, I am going to use the p-value method. So I am trying to copy this to a blank page so that we have it in front here. Okay, so that's the same example. And so what I'm doing is I am this time I'm using the p-value method. All right, so this time I'm using the p-value method. Okay, so the first step is the same. There's nothing changing. So the null hypothesis and the alternate hypothesis, that stays the same. the null and the alternate hypothesis, that stays the same. And so for the null hypothesis, I can just copy what I had from my previous slide, and that's that P was equal to 0.25, and that's where the claim was. And so for the alternate, it's not equal to 0.25. Okay, now step number 2 is still the same as before. It's the test statistic, and you still have to use the same formula. So it's the same formula as before, so P hat minus P over the square root of PQ over N. All right, so what you ended up getting here, I believe, was 0.67. All right, so that doesn't change. What changes is step number 3. Okay, so step number 3, and I'm going to try to highlight this, circling it. So step number 3 is what's different. And this is where I use a p-value. Now, the p-value, you already know what a p-value is because we've been working with this for a long time. That's just a probability value. Okay, so I have that definition for you a couple of slides before here, and I'll come back to it. But for right now, I'll just read it. So the p-value, it represents a probability value. You already know what a probability is. You know probabilities are always between 0 and 1. There are no probabilities greater than 1, and there are no probabilities less than 0. So no negative probabilities. You could have a probability that equals 0, and you could also have a probability that equals 1. But nothing greater than 1 and nothing smaller than 0. Okay, so you already know the properties for probabilities. This is what all this is. So the p-value, or your probability value, in this chapter, it's the probability of getting a value of the test statistic, which we already have, that is at least as extreme as the one representing the sample data. Now, we're always working under the assumption that the null hypothesis is true. So it's just a probability, and it's the probability of getting a test statistic that is at least as extreme as the one representing the sample data. So as extreme as the one we have right now, which is 0.67. So the probability of getting a test statistic that is as extreme as the one we have right now, which is 0.67. Now, if that probability is very small, if that probability is very low, then that results in rejecting the null hypothesis. If our probability is very, very small, that results in rejecting our null hypothesis. Because then the probability of getting a test statistic that is at least as extreme as the one we have would be very low. And that's strong evidence to reject the null hypothesis. Okay, so in our case, we can get the p-value by hand, and you can also get the p-value using your calculator. All right, so I'm going to show you how to do it by hand, and then I'll show you how to get it from the calculator. All right, so what we do here is the p-value is now our area. So the p-value, it's a probability value. Just like before, our p-value is then just an area. Okay, so let me go ahead and take you to the table. Right by the wording of your final conclusion, you have a diagram. And that diagram is for finding p-values. So let me show you what I mean. So in your pull-out formula card that comes with your textbook or that's in the ebook, you have p-value diagram here. And so that's what I'm going to follow. This is what I'm following. The first question says, what type of test is it? That's meaning, is it a left-tailed, a right-tailed, or a two-tailed test? Then then once I determine what kind of test it is, well then I follow, and then that's how I'm going to get the p-value. The p-value is just an area. It's either an area to the left or an area to the right of the test statistic, depending on the situation. So just like before, the probability is an area underneath a curve. Here, a probability continues to be an area underneath the curve. Okay, so I need to figure out whether I have a left-tailed, a right-tailed, or a two-tailed test. Now hopefully you remember that you go to the H1 to find out whether you have a left-tailed, a right-tailed, or two-tailed test. All right, so you say two tails. Okay, so we have a two-tailed test. All right, so let me go to the diagram, and what do we do for a two-tailed test? All right, so we have a two-tailed test. Is the test statistic to the right or left of the center? So if the test statistic is positive, then it's to the right. If it's negative, then it's to the left. So our test statistic is positive. So it's to the right. Okay. And so we're looking at this arrow right here to the right. So then my p-value is just twice the area to the right of the test statistic. And so I have to find the area to the right of my test statistic, and that is my p-value after I multiply it by 2. Now keep in mind that for two tails, you have an area, wow, that is a very bad curve. Let me try it again. If it's two tails, you already know that you're looking at two sides. All right, so if it's two tails, you already know you're looking at two sides. The area on the right and the area in both tails, they have an equal area. So the area on the right tail is the same as the area in the left tail. So you could find the area separately, but it's less work if you just find the area of one of them and then just double your answer. And that's all we're doing here. Instead of finding the areas in both tails, we're just finding the area in one tail and just doubling our answer, which is then the area in two tails. Okay, so our test statistic is positive 0.67. So I just have to find the area to the right because it's a positive test statistic. The diagram said to find the area to the right, and my p-value is twice that area. So I need to find this area. That's my p-value. All right, so then I have 0.67. That's my test statistic. It's on the horizontal axis. So if I look this up on a table, I should get an area. So which table would I go to? If I have a z, which is equal to 0.67, which table would I go to find the area? Right, it's table A2. Good. So table A2, go ahead and pull up table A2, look up 0.67 and see what area you get. Now remember, you have to make sure you get the right area, not the left, but the right. So look up 0.67 and tell me what you get. Okay, so what you're doing right now is you're going to table A2 and you're looking up the z-score of 0.67. And you're looking that up on your table. Okay, so I have an answer here. Okay, so you're giving me then 0.7486 is what you say, right? 0.7486. All right, now when you look up 0.67, remember the table always gives us the area to the left, which is not the area we need here. So we need to find the area to the right, and that should be easy to do, right? Because it's just 1 minus. All right, so it's going to be 1 minus 0.7486, and that's 0.2514. Okay. All right. So then our p-value, according to our guideline there, is that it's going to be twice the value in that area. So 2 times 0.2514. And so that gives us 0.5028. All right, so that's our p-value, 0.5028. Now, is there someone who did not get the area to the left to be 0.7486? When you look up 0.67, you should have ended up getting 0.7486. Okay, so you got something different. All right, so let me look. So you went to table A2, right? Okay, and so it's 0.67. So 0.6 is here. 0.0, so 0.67, so you have to see where those two meet. All right, so you see how it's 0.7486? So you have to look up 0.67. It's a Z, so make sure you see where they match up. Okay, so now you agree it's 0.7486? Remember that when you look up a Z, the table always gives you an area to the left. So the 0.7486 that we see here, that's the area to the left. We still have to find the area to the right. All right, so is that good? You agree on 0.7486? Yes? Okay. All right. So then what you see here then is the fact that we had to subtract that answer from 1. All right, so when we subtract from 1, then we get the area to the right, but of course we're not done. We still have to multiply by 2 to get our p-value. And the reason I multiply by 2 is because I'm just following what my definition says here. I know that I have a two-tailed test. My test statistic is a positive, so that's to the right. And so the p-value is twice the area to the right of my test statistic. So the p-value is an area. So for the p-value method, you have to find the area. For the traditional method, you were given the area as your significance level. So it's that step that is different, okay? Step number 3 is going to be different. Now, I could get all this on the calculator, and that's the nice thing about the p-value method is once you know where p-values come from and how to get them from, using the tables, you could use your calculator after that. So that's the nice thing about p-values is you could get to use your calculator. All right, so I'm just going to remind you about this table right here. Remember that the formula for our test statistic was the last of the formulas there, the 4th one. So on our calculator, we're going to select one prop z-test, and that's not only going to give us our test statistic, but that's also going to give us our p-value. So you have to go to your calculator, select stat, then tests, and then look for one prop z-test. So you can do that right now. I'm opening up the calculator just so that we could follow along here. But that's where I'm getting my information, okay? All right, so I'm taking you over to the calculator. I'm going to clear it. And so I want to go to Stat, right arrow over to Tests, and remember which one I was looking for? One prop, z-test. There it is, one prop z-test. Remember, there is a one prop z-interval, so don't get confused with that one. Make sure you're looking at the right one. And the first line that you're looking at, that is the value of, that's the value that's in the null hypothesis. Okay, I had lost the sound there for a minute, so I don't know what the last thing I said was. I was going to show you how to do that on the calculator. All right. So we looked at how to find the p-value. And so now I'm just going to go ahead and use the calculator. Is everybody okay now? Can everybody hear me? All right, okay, lost the sound there for a minute and I looked over and there's no sound. Okay, so what I'm doing on the calculator is I went ahead and I just followed the instructions that I gave you in the notes. If you look at the whiteboard here, I'm just looking at the instructions that I have there. So when we're using that formula for test statistic, that corresponds to this command on the calculator. So what it says up here is that I'm going to go to Stat, over to Tests, and then select the one prop z-test. And that's what I'm doing. All right, so that's where I'm at right here. Let me just go ahead and clear it because I don't know where I lost the sound. All right, so just go ahead, go through it one more time. And so I'm going to go to Stat, and then right arrow over to Tests, and it's the one prop z-test, number 5 on my calculator. So I'm going to select one prop z-test. You have to be careful because there's also one prop z-interval. So you want to make sure you're choosing the right one. One prop z-test is what I want. And then on the screen, the first line, that's the value of my population proportion that's in the null hypothesis. So what is the value of p in the null hypothesis? That's the first line. So that's 0.25, I believe. The next line here, that's your x. And x in this example was the number of yellow pods. So yellow pods, I think we had 152. N is your total sample size. That was 580. And the next line was the inequality in your alternate hypothesis. So what's in your H1? In our case, it was not equal to. So you go over where it says not equal to and just press enter to select it. And then at the very bottom it says calculate, so you're going to go ahead and select it and then press enter. And it just gives you a screen that we're going to find very helpful. Let me go ahead and move it over to the whiteboard. All right, so there are a couple of things that we're looking at here. first of all, the test statistic is given to us. So just by doing that one prop Z test, we already know our test statistic. If you remember, that is the test statistic we were talking about over here, 0.67. And our p-value is 0.50, so let's see if our p-value is close. Okay, it's pretty close. It's not exactly the same. So our p-value is the one that says p. We have two. We have p hat and then p. And it's hard to tell the difference. I think you could probably see there's something on top of this p. That's supposed to be p hat, but it's hard to see on the calculator. So just remember your p-value is right below the test statistic on the calculator. All right, so here's our p right there. That's our p-value. So I'm going to write it here. So our p-value is 0.5021 if I round to 4 places. 0.5021. So that's our p-value. I used the calculator to get it. Let's see how close it is to the p-value we had when we did this by hand. All right, so on the calculator, I'm going to go ahead and put calc, C-A-L-K, for calculator, and I believe it was 0.5021. So that's pretty close. So the p-value on your calculator is pretty close to the p-value that we had from using the tables. Now, it does not matter to me which you use. Hopefully you'll be using the calculator because it's obviously less. I'll get you the p-value a little faster than the tables. So if you can, whenever possible, use your calculator to get your p-value. It's important that you know how p-values are obtained, so that's why I did this by hand, so that you know how we would get a p-value. Now you know that you can input all your information and get the p-value using your calculator. Okay, so that's the new step. That's how we find a p-value on our calculator. Okay, and I did it by hand as well. All right, so the next step, step 1, 2, 3, the next step is writing our conclusion. I need to figure out whether we reject the null hypothesis or fail to reject the null hypothesis. Now, how we come to that conclusion using the p-value method is this. If your p-value, let me write this in a different color. So if your p-value is less than or equal to alpha, which is our significance level, if it's less than or equal to alpha, which is our significance level, then we will reject the null hypothesis. So using the p-value method, the way we know we're going to reject the null hypothesis is based on our p-value. So if our p-value is less than or equal to alpha, which is our significance level, then we are going to reject the null hypothesis. Now remember, a long time ago I actually had defined to you what alpha is, what that significance level was. That significance level is a probability. So alpha is also a probability, which is an area under a curve. That's how we were doing it with the traditional method. But alpha is also a probability. And it's a probability that the test statistic, well, we talked about how it was the probability that the test statistic will fall in the critical region where the null hypothesis is actually true. So alpha is the probability of rejecting the null hypothesis when it's true. So alpha is the probability of rejecting the null hypothesis when it's actually true. All right, so in this case, alpha is 0.05. So you compare your p-value to alpha. Okay, so in our case, is 0.5021 less than or equal to alpha? What do you say? So I am comparing my p-value, 0.5021, and I'm comparing it with alpha, which is 0.05. So is my p-value less than alpha? What do you think? All right, so it's not less than, in fact, it's greater than. So it's not less than or equal to alpha, so I cannot reject the null hypothesis. So I would have to say that we fail to reject. I have to fail to reject the null hypothesis because my p-value is not smaller than alpha. So that's how I come to my conclusion using the p-value method. I'm always comparing the p-value to alpha. P-value is a probability. Alpha is also a probability. And remember, I said that alpha was the probability of rejecting the null hypothesis when it's actually true. So we're comparing our probability, our p-value, to that alpha. All right, step 4, that's our conclusion. So here we ended up failing to reject. Now I'm wondering what we ended up with in the previous example where I just used the traditional method. Did we also get failed to reject? We did get failed to reject. Okay, so then it's the same conclusion because our null hypothesis still has the claim and we did fail to reject, so it's the same conclusion. I can go and copy and paste this over, it's the same conclusion. All right, so there was a question here about our significance level, and the question is if our significance level can be higher than 0.05. Yes, there are some problems in the homework where your alpha is something other than 0.05. I've seen significance levels of 0.10 and 0.01, so it could be something other than 0.05. So you just have to read the question and see what they're telling you. All right, that is very tiny. I was just trying to save some time and just copy it over. Let me try it again. Somehow I lost my ability to make that bigger. All right, well, it's, I guess, enough to know that we would get the same conclusion. So let me just redo it. Oh, I found it. Okay, perfect. There are a lot of tools here on my on my desktop. Sometimes they get lost, but there it is. Okay, so there is not sufficient evidence to warrant rejection of the claim that the proportion of p's with yellow pods is equal to 1/4. So that is the same conclusion as before, because once we know we're going to fail to reject the null hypothesis, then it's just a matter of following our conclusions. So our hypothesis, the final wording of our conclusion from this diagram that I had already showed you. So did the original claim contain the condition of equality? It did, because it was in the null hypothesis. Did we reject the null hypothesis? No, we failed to reject. So we're in the same box here. It's still the same final conclusion. All right, so I solved this problem using the traditional method of hypothesis testing, and then I solved the problem using the p-value method of hypothesis testing. So again, this was the p-value method. Finding a p-value means that you're going to find the probability that of being to the right of the test statistic or the left. So it depends on the diagram. So it's finding an area. And again, that p-value is just the probability of getting a value of that test statistic that is at least as extreme as the one that you got from the sample data. And it's always under the assumption that the null hypothesis is true. Okay, so I am going to take you back to some of the definitions that I skipped earlier, because I was already going over them, but just so that you know, it's already printed out for you. It's on the notes. Okay, so the first one that I skipped was the one with p-values, and that's the one I kept referring to right now. So what is a p-value? It's a probability. P-value is a probability, and you want to make sure you write p-value. You can't just write p, because if you write p, that's referring to the population proportion. So you have to make sure you're writing p-value. So it is just the probability of getting a value of the test statistic that is at least as extreme as the one that was obtained using your sample data. And you always reject the null hypothesis if your p-value is small. And how we determine if our p-value is small is we compare it to alpha, which is our significance level. All right, so with the p-value method, the way we make our conclusion about whether or not we're rejecting the null hypothesis is by comparing it to alpha. Alpha is the significance level, and it will be given to you. If it's not given to you in the problem, do you guys remember what the default is? What would we use if our significance level was not given to us in the problem? Right, 0.05, that's the default. So if you're not given the significance level, the default is 0.05. Right, so look at the difference between our conclusions. This is what we conclude. This is how we conclude to reject the null hypothesis if we're using the p-value method. It's always taking the p-value and comparing it to alpha. If it's smaller than alpha, then you reject the null hypothesis. If you were using the traditional method for hypothesis testing, in that one you reach your decision in a different way. Here we reject if our test statistic falls inside the critical region. So for the traditional method of hypothesis testing, you're comparing your test statistic with your critical value to see if your test statistic is in your critical region. And that's how you reject the null hypothesis. So there's two different methods, and there's two different definitions for how we reject the null hypothesis. And it all depends on the method that you're using. So you have to be very clear as to what method you're starting with. Are there any questions? Okay then, so with the p-value method, again, we're comparing your p-value with alpha. If it's less than or equal to, then we reject the null hypothesis. So what is this alpha I keep talking about? I kept going over at least I kept reading you the definition, right? But what is alpha? So alpha is used to represent a probability. We already talked about how alpha represents a probability, and in the traditional method of hypothesis testing, alpha is the area and the tails. So area is probability. So alpha is used to represent a special type of error, and we call that a type 1 error. And a type 1 error is the mistake of rejecting the null hypothesis when it's actually true. And so that's what I kept talking about. Alpha is the probability of rejecting the null hypothesis when it's actually true. So we don't really want to reject the null hypothesis if it's actually true, right? So we want to make sure alpha is pretty small. So we don't want to do that. We want to make sure that probability is pretty small. But if you make alpha too small, then you run into other problems. But in this case, we call a type 1 error the mistake of rejecting the null hypothesis when it's actually true. And alpha is used to represent the probability of a type 1 error, the probability of rejecting the null hypothesis when it's actually true. Now we have a type 2 error as well. And a type 2 error is the mistake of failing to reject the null hypothesis when it's false. So it's the opposite. It's failing to reject the null hypothesis when it's false. So when null hypothesis is false, we would hope that we would reject it, or at least that our evidence would be such that at the end we would reject. But if it's not, then we've made a type 2 error. So again, the type 2 error is a mistake of failing to reject the null hypothesis when it's false. So beta represents a probability of making a type 2 error. Beta is the probability of failing to reject the null hypothesis when it's false. Now, this table hopefully will help you understand what I just said. So here we have the true state of what's going on, right? The true state of nature. So this is what's actually happening. So if the null hypothesis is actually true and we fail to reject the null hypothesis, then we've made the correct decision. So when the null hypothesis is actually true, then we hope we fail to reject the null hypothesis. And we've made the correct decision. And if the null hypothesis is false, then we hope that we reject the null hypothesis. So if the null hypothesis is false, then hopefully we reject the null hypothesis, and that's the correct decision. If it's false, then hopefully we reject it. If it's true, then we fail to reject it. Okay, so we've made a correct decision if we're in these two boxes. Now I just noticed a little mistake here. This one says we fall to reject the null hypothesis. No, we do not fall, we fail. We fail to reject the null hypothesis. That's what that's supposed to say. Okay, so a type 1 error is made when the null hypothesis is true and we reject it. If the null hypothesis is true and we reject it, then we've made a type 1 error. And the probability of rejecting the null hypothesis when it's actually true is alpha. Now another error can be made if the null hypothesis is false and we fail to reject it. That's called a type 2 error, and the probability of making a type 2 error is represented by beta. All right, so this alpha that you keep reading about in the examples, that's what it means. It's the probability of making a type 1 error, which is rejecting the null hypothesis when it's actually true. All right, now what is the relationship between alpha and beta? And we're not going to get that far, but let me go to the previous slide. So there's a way of controlling your type 1 and your type 2 errors. Right? So you don't want to make errors, of course, or you want to minimize making those errors. So for any fixed alpha, so say you fix alpha to be 0.05, if you fix alpha, an increase in the sample size will cause a decrease in beta. So if alpha is fixed and you increase your sample size, then you're going to decrease the probability of making a type 2 error. So that's how we can control making a type 2 error, but it has to be for a fixed alpha. So if you fix your alpha, increase your sample size, you're going to decrease the probability of a type 2 error. For any fixed sample size n, if you decrease alpha, unfortunately that's going to increase beta. So if you decrease alpha, you're going to increase beta. Conversely, if you increase alpha, then you're going to decrease beta. Right? So if you increase one, the other one's going to decrease. If you decrease one, the other one's going to increase. So there's a relationship between alpha and beta. So both of them represent the probability of making an error, which you want to minimize. Now, to decrease both alpha and beta, then you can increase your sample size. Increasing a sample size will help us decrease both the probability of a type 1 error and the probability of a type 2 error. So there are some ways of controlling type 1 and type 2 errors. And this slide just talks about all the different possibilities. Now, remember I said there's a relationship between alpha and beta. We have something called the power of a hypothesis test, and this is the probability of rejecting a false null hypothesis, which is computed by using a particular significance level alpha and a particular value of the population parameter that is an alternative to the value assumed true in the null hypothesis. All right, so a better way to say this is that the power of the hypothesis test is the probability of supporting an alternative hypothesis that is true. Right, so there is a relationship between that alpha and the beta. Again, an increase in one decreases the other, and a decrease in one increases the other. Okay. So I think I've covered so this is to make sure I covered everything. We talked about test statistics. We set up our null and our alternate. We set up our null and our alternative hypothesis. We talked about the different formulas for test statistics. It all depends on the population parameter that we're testing. We talked about significance levels. Alpha is their significance level. Alpha represents our significance level, and alpha is the probability of rejecting the null hypothesis when it's actually true. That's a type 1 error. We talked about p-values today. And there is a couple of examples I think I had for you. Let me look for them. These were finding p-values. So I have a couple more. Just a couple more examples just to practice p-values. All right, so here it is. There's the first one. Okay, so we're going to just take some time here to see if we understand how to find p-values. All right, so the only purpose of this exercise is just to find p-values by hand. You will not be able to do these on the calculator because I didn't give you enough information to do these on the calculator. All right, so just finding p-values by hand. Okay, so what I'm doing here is I am using this procedures that I talked about earlier. Okay, so that's what I'm using. That's all I'm using. All right, so for this first one, I first have to decide whether I'm looking at a left-tailed, right-tailed, or two-tailed test. All right, so what in the problem tells me what kind of test I have? Let's see if I can find it here. All right, so a significance level of 0.05 is used in testing a claim that p is greater than 0.25 and sample data results in a test statistic of 1.18. Okay, so you don't have to set up the null and the alternate, but I like to do that just so that I have a better picture. If the claim is that p is greater than 0.25, that must go in the alternate. So that means the null is equality. And so our test statistic here, our TS, is a positive 1.18. All right, so I'm going to go back to my tables here. And the first question is, what kind of test is it? So where do we look to find out what kind of test we're looking for? So is it left-tailed, right-tailed, or two-tailed? Where do I look? All right, so the H1, that's where I look. Okay, so I'm looking at the alternate hypothesis, and it's a right-tailed test because it's pointing to the right. So that's all I get from here. It's a right-tailed test. All right, the next thing I need is, if it's a right-tailed test, then it says the p-value is the same as the area to the right of my test statistic. All right, so a right-tailed test means that my p-value is equal to the area to the right of my test statistic. So my test statistic is 1.18, 1.18, and the area here, that's my p-value. So which table do I go to find the p-value? Which table do I go to look up the 1.18? All right, so make sure you're in the right table, table A2. Yes, that's the correct one. So in table A2, you are going to look up 1.18. 1.18. When you look up 1.18, well, here's my table. 1.18, so I looked at 1.1, which is right here, and the 8 is up at the top. So 1.1, and the 8 is this column. So do you guys agree on 0.8810? Now that's the area to the left, right? It's not the area to the right. It's not what I'm looking for, but that will help me. So 0.8810 is the area to the left, so let me label it as such. So 0.8810, that's the area to the left. And right, I have to subtract that from 1 to get the other side, right? So 1 minus 0.881 would be the right side. So my p-value here is equal to 1 minus the area to the left, which is 0.1190. So my p-value is 0.1190. Now, I don't have enough information to do this on the calculator because I don't have sample data. So the only reason I'm doing this exercise is just to practice how to find p-values by hand. Now, in this case, if I had to continue, the p-value is less than, I have to find out if my p-value is less than alpha, right? So I would know whether or not I'm going to reject. All right, so if my p-value is less than or equal to alpha, then I'm going to reject the null hypothesis. That's how I make a conclusion using the p-value method on what to do with the null hypothesis. So do I reject the null hypothesis in this case? All right, yeah, so that's not greater than alpha. That's actually larger than alpha, which is 0.05. So fail to reject. Now, I wasn't asked to do that here. That's just extra. We're just finding p-values using the information given. All right, so just practice finding p-values. Now you know how to find p-values on your calculator. If you were given the sample data, you could find that. But for this one, it's just by hand because we don't have any sample data. All right, let's do one more. All right, how about this one? So I want you guys to find the p-value here. So let's go ahead and set it up. The claim is that p does not equal to 0.25. So then in the null it's equal. Okay, so our test statistic, our TS, is 2.34. That's our test statistic. And so I just go back to that diagram I was talking about. And I know it's going to ask me about whether it's left-tailed, right-tailed, or two-tailed. So I know based on what's in the H1, this is two-tails. So based on what's on the H1, we know we have two tails. So if we have two tails, I know how to answer when I get to the table. Okay, so now let me go ahead and take away the other stuff that I have here. We need to know what type of test this is. We know it's a two-tailed test. Now the question is the test statistic to the left or to the right of the center? So if it's to the right, it's a positive number. If it's to the left, it's a negative number. So I think it was positive, right? So then our p-value is equal to twice the area to the right of the test statistic. All right, so just remember that's our process. And so here is my distribution. Our test statistic is 2.34. So our p-value is the area to the right of our test statistic. So now if you're going to table A2, you're going to look up 2.34. So table A2, look up 2.34. What do you get when you look up 2.34? Okay, so I see two of you ended up with 0.9904. Okay, so 0.9904. So you agree that's the area to the left. We want the area to the right. That's our p-value. Well, at least our p-value will be twice the area to the right because it's a two-tailed test. So the area to the right would be 1 minus 0.9904. And following the diagram that we looked at earlier, the p-value is twice the area to the right. So it's twice 0.0096. 2 times 0.0096. Again, I'm doing that because I'm just following the table that we were looking at, this procedure for finding p-values. So remember that a p-value is a probability. Probability is area underneath a curve, and that's what we're finding here. We're finding the area underneath the curve. And the p-value is just the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data. And our p-value here, if you continue, is 0.0192. Now, that's all we're being asked for in this question. That's it. We're done. But I'm just curious, based on our p-value, do we reject or fail to reject the null hypothesis? Okay, so 0.0192 is definitely less than 0.05. Good, yeah, so we would reject here. We would reject the null. So these are just exercises in allowing us to go through the process of finding p-values. I did find the p-values by hand. I didn't use the calculator. You could use your calculator if you have sample data. You could use that command that I showed you, the one prop z test, to help you find your p-values. Okay, now I just did a few examples. Of course, you want to make sure you get that homework started because you might find something that's slightly different than what we went over. For example, instead of using table A2, maybe you had to use table A3. So make sure you go through that homework, and if you have any questions, make sure you let me know. Either post your questions on the discussion board, or you can wait to ask me at the next lecture. You can let me know what questions you're having issues on. All right, so are there any questions right now? All right, so let me go through my notes, make sure I covered everything. Okay, the only other thing I see is just remember that you need to be careful about your P's. The p-value and P, they're different things. So when testing claims about the population proportion, the traditional method and the p-value method are equivalent, and they're going to give you the same result. However, when you use confidence intervals, so it's not the case. Okay, so this is not what I wanted to say. That's something else. What I wanted to say was that one of the confusions is P and then p-value. So you want to make sure if you're talking about a probability value that you're using the correct notation. You can't just use P because P means population proportion. So you don't want to make that mistake. Okay? All right, so let's see. I think I went over all the main stuff. Yeah, so your homework is already up there. There is a question about the homework. Your homework should already be up there, and you do have something due. So you want to make sure you get that started as soon as possible. I know I made it available earlier. I thought it was last week, but it might have been today. But yes, you do have homework. Okay? All right, so I will stop there, and we will meet next time, and I will continue talking about confidence intervals. Let me just make sure that I have printed out the roster here. So again, I like to know who's been coming to class. Now, remember, in order to get credit, you need to do the lecture problems. So today you have 2 questions for your lecture assignment. And those 2 questions, they're a little bit more, they have different parts to them. So you want to make sure you get that started as soon as possible. All right, I'm just trying to print out the list. There it goes. All right, and I'll just leave the last example I was writing on there, okay? All right, so I'll talk to you at the next lecture. We will continue Chapter 8 stuff.